Hey guys, it is exciting. I am back on the smartboard, so that's cool. And it is the last notes of the year, baby. So we are doing notes for section 5-6. There is a lot of review here and maybe a couple new things. Sadly, it is not the most exciting notes. And my advice is write small. Okay, but last notes of the year, tough it out. Here we go. All right. So we're going to review some things we've learned. We started with arithmetic sequences. Better do this. Here's an example of an arithmetic sequence, right? And the first question is, how do you recognize if a sequence, a table, a graph, or a situation is arithmetic or not? And the answer is, it is arithmetic if there is a common difference between each term and the next term. All right. How do you find the common difference for an arithmetic sequence? Easy, right? Subtract any term. Let's put that in parentheses. Subtract any term minus the previous term. That's an R. Any term minus the previous term. How do you write the explicit formula and recursive formula? Okay, so first we're going to do explicit. The explicit formula is T of n equals A plus B times n. A equals the zero term. B equals the common difference. Right? Wouldn't hurt to say T of n equals any term, and n equals the term number. All right. And what about the recursive? The recursive formula looks like this, right? T of 1 equals blank. T of n equals T of n minus 1 plus blank, where this is the first term and this is the common difference. And you know, I was thinking about it tonight. I was looking at things. I have seen, not that I'm never going to do this to you, but just for your information, I've seen this listed as T of n plus 1 and this as T of n. Right? So this is still the previous term before T of n plus 1, right? N would come before n plus 1. So we're still talking about what do you do to the previous term. All right, next up, how do you determine the 100th, I made up 100th, or some random number term of the sequence? And all you do, of course, is use the explicit formula or equation and sub 100 in for n. the term number. All right? Next up, how do you determine if 420 or some random number is a term of the sequence? All right, so again, use the explicit formula. Put 420 in for T of n, right? It doesn't go in for n, it goes in for the whole thing, T of n. And solve for n. Then, if 420 is a term of the sequence, n will equal a positive whole number. Boom! Can we graph the sequence and describe the graph? All right, so here's something for you. Being linear could use the slope and y-intercept, right? The slope is the common difference. And the y-intercept is the zero term. And of course, you could graph it by using those, or you could make a table from the equation. But the bigger thing is, we've gone over describing a graph. And there are many different things we can now do to describe a graph. Linear, nonlinear, right? Let's see, line or exponential curve, right? Positive, negative. And positive or negative kind of means it's either increasing or decreasing. Let's see. You could give the x and y intercepts when you describe a graph. You could give the domain and range when you describe a graph. And I left out one. And last, darn it, I'll put it over here, I guess. Continuous or discrete. Boom. Those are all things you should be able to talk about when you look at a graph of a function, a sequence, a situation. Lots of things there, right? Okay. Next up, we move on to the geometric sequence. For the geometric sequence, how do you recognize if a sequence, table, graph, or situation is geometric? Here we go. It is geometric if there is a common ratio between each term and the next term. How do you determine the common ratio? Do you know the other names for it? Can you write it when it's a percentage? All right, so let's start with the first one there. Common ratio equals any term divided by the previous term. Boom, that's one. Other names for the common ratio. The multiplier, the growth rate, or the growth factor. All of those are other names for it. And can we write it when it's a percentage? Well, of course we can. If you were going up 5%, right, it would be 1 plus the percentage. And if you were going down 5%, it would be 1 minus the percentage. How do you write the explicit or recursive formula for the geometric sequence? All right. Explicit. The explicit is T of n equals AB to the n, where A is still the zero term, and B is the common ratio. And recursive. Recursive. There we go. And so the recursive is T of 1 equals blank, T of n equals T of n minus 1 times blank, where, of course, this is the zero term, and this is the common ratio. Okay, we are flying here as fast as I can. How do you determine the 100th term or some random number? All right. Yeah, I guess we'll write it. It won't take a second. Use the explicit formula sub 100 in for n, solve for T of n. All right? How do you determine if 420 or some random number? I'm not writing it again. I'm giving you a break. Same as arithmetic. How do you graph the sequence? All right. So if I'm graphing a geometric, probably the easiest way right now for us to graph a geometric is make a table. Right? And how do you describe the graph? All right, so to graph it, I think you want to make a table. To describe the graph, same way as arithmetic with, right? Where you want to go through all of these things. All of those things help you describe a graph, whether it's arithmetic or geometric. All right. Did I finish that? Nope. I'm here. I'm moving on. Here we go. All right. So now we're going to look at exponential equations. We just looked at these in the last section or two. Right? Exponential equations are basically the same as a geometric sequence and all that stuff, except for one thing. What is the difference between a geometric sequence and an exponential function? I'm going to write two things here. Exponential functions have a domain and range of all real numbers and are continuous graphs. Whereas geometric sequences are discrete and have a domain of positive whole numbers. So the big difference is geometric sequences, always a discrete graph, and the domain is limited, whereas exponential functions, continuous graph, and you can use any x value in all exponential functions. Can we write exponential equations for application problems? So this is why we wanted to learn about exponential equations. They're exactly like geometric, but they include a larger domain. But they have the same equation as a geometric. So let's write that down over here. Same as geometric formula, same as explicit formula for geometric, y equals ab to the x. But notice I did not put it in function notation, though I could have. And a is still the zero term, and b is still the common ratio. Although usually we call it the growth rate or the growth factor when we're talking about an exponential function instead of a geometric sequence. So, better if we call it the growth rate. All right. So could we do that for this? Jim started with $5,000. So it's going to look like this. But my starting amount is $5,000. So it's going to be 5,000 times, and it's growing by 7%. So that's 1.07 to the x. And I think in these problems, it's important to make sure you know what the x and the y, or you write down. Not that you know it, but you write it down and communicate it. What do the x and the y stand for? In this case, the x stands for years, and the y stands for total money, I guess. All right, so I have written the equation. And on your homework, I can't remember if it's this homework or the next one, I would say this is the general equation for the situation. And now we're going to write it specifically for this situation. How much will Jim have in 10 years? So 10 years, that's the x value. It'd be y equals 5,000 times 1.07 to the 10th. This is how I show the calculation I'm going to do to get the answer. And then I actually do the calculation, and you'd be surprised to know we get $9,835.76 approximately. All right. And then we're almost done. What is the difference between exponential growth? Uh-oh, I feel like I skipped something. Sorry. Here it is. How much fun? Oh, no, I just forgot to copy it. It's so sad. So in your notes, can we graph? Boom. Apparently, I forgot to put that on the smartboard. We can, same as geometric graph, but decide continuous or discrete. And that continuous or discrete will depend on what your variables represent. Do fractions make sense or do they not make sense? But if you're just graphing a general equation, always continuous. All right, finally then, what is the difference between growth and decay? This is quick. Okay, exponential growth means the multiplier or growth rate is greater than 1. So in our formula, y equals ab to the x, b is greater than 1. And if b is greater than 1, we get an increasing graph or growth. Decay, multiplier is between 0 and 1. By the way, this graph looks like this. And when you have decay, let's see. So in this case, for my equation, y equals ab to the x, the b value is less than 1, but it's got to be greater than 0. And then you get decay. You get a graph that looks like this, where whatever you have is going down. All right, that is the last notes. Oops. Good luck. Sorry, it wasn't an exciting one, but I will see you guys maybe tomorrow, maybe after break. Bye-bye.